Esperto. Sono molto contento di essere qui. I think I will speak in English. It's not a problem, but obviously there is no problem at all to have discussions in Italian if you want questions in Italian after the presentation. It's just that for me it's a bit easier because if there are some technical terms, I know them. I use them in English in general. So, I want to discuss a little bit what I call sometimes the new artificial intelligence. And you know, in intelligence there are these quotation marks that matter a lot, and that we will try to discuss in the second part of the discussion. And but I want first to address the other words, in particular the new artificial intelligence. Why new? And it's an interesting topic that actually the contemporary trend of artificial intelligence, it dates back to a very well-defined moment, which is 2012. 2012 is really the moment in which, for the first time, an algorithm based on neural network was much better than any other algorithm at a competition which amounts to categorizing images, which is there with this ImageNet database, 1 million images, 1,000 categories. You want to be able to analyze the images and say to which category it belongs. Is it an audience in a conference hall? Is it a restaurant room? Is it a pizza? Is it a dog? Etc., etc. And it's interesting to see that this kind of competition, it looks a bit remote from academic world, but it triggered a lot of activity, and at some point, thanks to that, it was possible to identify a breakthrough. That is, in 2012, for the first time, there was this competing neural network that succeeded in having one half of the errors of all the other algorithms. So it was a decisive breakthrough. And in 2013, all the algorithms that were competing were based on this same idea. So it was a big shift. We will discuss that a lot because it's also a kind of paradigmatic shift. It's a moment in which one starts to use algorithms which are based on what is called machine learning. I will discuss that a lot, which means that the algorithm is not fully programmed. It is trained to program itself, basically. And so there was this big success, but this came more or less 70 years after the beginning of AI, and even 50 and something years after the beginning of neural networks. Neural networks were already there. There is an interesting, nice paper by Frank Rosenblatt in 1957. 1957, Rosenblatt has this neural network, which now looks a bit elementary, in which you have an input layer and an output layer, just one layer, and it's called the perceptron. And it was famous at that time. There was an article in the New York Times saying, well, thanks to this new invention of the Navy, I think the Navy was supporting the research of Rosenblatt, we will soon have computers that are able to speak, think, have concepts and consciousness. 57 in the New York Times. We are still not there. But so there were big hopes. There was a big wave of hope also in the second half of the 80s and the 90s. There were a lot of people working on neural network. I was among them, so I remember that period very well. And then it did not really deliver, in the sense of it already appeared at that time clearly as a new way of organizing a computer, something very different of organizing a computer with respect to the usual Turing machine-based argument, but it did not deliver in terms of application. And so 2012 is the first time in which it seems to be something that maybe will have some practical application. And then the thing that it went very, very fast. I mean, immediately, as I say, in 2013, everybody was adopting that. And very soon, there were training of these image detection algorithms in order to analyze medical images, for instance, radiographies, tumor pictures, etc. And this is still probably one of the main applications, the most direct applications, beneficial applications. At the same time, there was face recognition, and face recognition means the possibility to control populations, etc., etc. So here I just mentioned it now, but we will come back to that because it already has the two faces of how you can use the way of analyzing images. And then it had another thing that was pretty obvious from the very beginning. Say, well, if you are able to analyze an image, it means you are able to segment it. So I give you this image and the algorithm is able to say, well, there are faces of people who are watching, that's a conference, here are the faces, here are the chairs, here are the room, the windows, etc. And you can do the same thing in the street. And so as soon as you do that, you say, well, then now I should be able to solve the problem of self-driving cars. And I remember that immediately one of the first applications that came to mind was self-driving cars. And as you have seen, self-driving cars, they start to be around in California, but not yet very widespread, and there are still obstacles, there are still problems, and we will discuss it a little bit. So this was 2012, and since then there was every third year there was a new revolution, something unexpected. I will give you a few benchmarks. 2016 is the moment in which an algorithm based on deep networks called AlphaGo wins the Go competition against the world champion. This was unexpected because we knew for many years that chess had been, there had been Deep Blue and IBM had won the chess championship again against Kasparov. But in some sense, Deep Blue, which was back in the 90s, in 1997, Deep Blue was a kind of brute force analysis. That is, in chess, you could, with brute force, with a big enough computer, you could analyze what will happen in 5, 6, 7 exchanges from now. And so you can have a depth that is very difficult to have. And then you analyze all of them, and then you can have something. The Go game was known as it was known it would be impossible to do it by brute force, because the number of possibilities of how you play is much larger at each step. And because it grows exponentially with this number, so it's a much faster increase. So it could not be brute force, and so the fact that it could be possible to train this machine was a big surprise and breakthrough. And then there was soon after, so maybe 1 year or 2 years after, probably 17 or 18, there was the new release of AlphaGo, which was AlphaGo 0, which was another surprise in the sense that in AlphaGo 0, AlphaGo was using the whole data of all the Go games that have ever been played. Okay. So in some sense it was getting inspiration from what the champions have been doing for centuries, etc. AlphaGo 0 was trained from scratch without any knowledge of any game. It was just knowing the rules of the game and basically playing strategies against itself. And so if you have a strategy that wins against the other, you gave it more reward. And so it's reinforced, and it's called reinforcement learning. And so with that, you can develop completely new strategies and new ways of playing that were not known before. So that was a Go. In games, there were a lot of progress that I don't know much about, but in 2019, there were the programs that were able to play very high-level poker, and then there were video games, including video games in which you need to interact with others, not only have your own strategy, but have your own strategy which has to be mixed with others. So that is for games. Then the other breakthrough that I want to mention is 2020. 2020 is AlphaFold. AlphaFold is the big breakthrough for science. It is the moment in which we have a deep network which is able to analyze the shape of protein. Not completely solved, but let's say it's a big step towards solving the protein folding problem. So you have the sequence of amino acid of a protein, and from that sequence you want to understand how the protein takes its shape. It will fold in 3 dimensions. This fold is very important because, as we know, once the protein is folded, it is through the amino acids which are at its surface that it will interact with other proteins. So the whole construction of biology is due to what are the exposed amino acid in a folded protein. So the shape of this folding is something very important, something on which there had been a lot of work in thermophysics, thermochemistry, basically works in which you have a lot of fundamental ingredients. You know the interaction, the electrostatic interactions, you model them, you simulate them on very big computer, you try to see how it folds. That was done for many years. And all of a sudden, there was this new program that did not do that at all. It was based on training, I will explain that later on, but based on training on a big database of proteins on which we know the sequence and how they fold. So we had a lot of examples, carefully worked out by a lot of researchers before. And then basically what the program does is some kind of statistical analysis of this database, from which it will infer the rules of the game, which are not really directly inspired from the physics. So I am a physicist, so I mean, it's the surrender of physics against statistics in some sense. Although statistics is based on a lot of preliminary physical studies and could not have existed without it. So that was 2020. Then 2022, November 2022, we all remember the release of ChatGPT. In general, the generative models. Generative models is how to generate images, how to generate text. And when you generate text, you are able also to translate. And I think it was one real novelty. In some sense, as I said, there were many waves of AI, including several waves of neural network studies. And most of the studies on contemporary neural networks, the ones that are used in the modern AI, they were based on theories and ideas that were already here in the 90s. But there was one aspect that was not worked out that much in the 90s, which was a generation. This idea of generating data and generating fake data. So the idea of generation is you take a bunch of images of conference rooms and you want to generate a new one, which with characters that have never been seen by the machine, that are invented, a setup which is invented, etc. But it has to be realistic. And it's a very interesting aspect because it starts to put the focus not so much on the task, which is classification, segmentation, strategy, the things that we saw before in image analysis, in game, etc., but on the structure of what I call the structure of the world, the structure of the world that you feed your network with, the structure of the data. If you have a database of images of conference halls, what is common to all that? And so this is, if you are able to generate a new one, it means that your program has been able to abstract something about what it means. Not what it means, sorry, what it is. So this is the arrival of generative models. I will have a dedicated chapter to language and to large language models, because I think it's something that is a big, I mean, first of all, it was a big surprise, but it's a big challenge. It's a big challenge for understanding and positioning it with respect to the scientific activity, and maybe also some philosophical consequences. I'm just a poor physicist, so I'm not good at philosophy, but I will nevertheless ask some questions for you to answer, because I know you have to answer questions in the afternoon. So these were just a few benchmarks. I mentioned them because I want to stress one thing. I think that none of these breakthroughs, and they are real technological breakthroughs, I mean, things that seemed impossible. And none of them were expected. None of them has been foreseen. I mean, very optimistic people would have said, oh, maybe in a few decades it will be possible to. But then 2 years later, you have something that you have the folding of proteins. It solves. It's a very important. I mean, it's something. You know, the 2020 AlphaFold. It will be a benchmark in the history of science because it's the moment in which we start to have a tool which helps us to read the book of biology. I mean, if you are able really, it's the first step toward the function. The shape is the first step towards knowing the function. So if you are able to have a kind of analysis of the language, which gives you from a sequence of amino acids or the sequence of base pairs which code for it in the DNA, and you read that and you are able to know the shape and how it will interact with the others, it means that you have understood a large part of how biology works. So that is, I think these are very major breakthroughs, not foreseen. So sometimes I say that AI should be remembered for not so much for artificial and intelligence, but the A should be for acceleration, and the I should be for ignorance. So acceleration, I have started to document it a little bit, and ignorance, I will try to show it later. So what we have seen are very important technological breakthroughs.
Can you ask a question now?
Of course, please. So I should have said that. Any question, any interruption is more than welcome.
So, computational, I'm a physicist, so talking about computational physics, but it could be computational NP1 was also a breakthrough with respect to calculations on pen and paper, let's say. How would you grade, if the question makes sense, artificial intelligence in that sense? It's another step, so it's another advancement with respect to computational techniques, or it's of a different level with respect to that?
I think I personally characterize it as a major new step of computational science, let's say, in some sense. That's how I view it. I think that, well, as you know, I was in the generation who saw the arrival of scientific computing. And I remember that before that, there were theoretical physics, experimental physics. Gradually, they started to be computational physics as a third way. It was not so easy, actually, to find its way. I mean, I remember there were a lot of people, some of my colleagues, theorists, there was a lot of contempt, towards these numerical methods, etc. Then gradually, people realized that the numerical methods was also a way to sometimes bridge the gap between theory and experiment. That in physics, we have the tradition of modeling. And the tradition of modeling means taking the reality, and the reality is so complex that you have to cut off some things that are not essential in order to understand the essential ingredient of what you want to study. That's modeling. But of course, modeling, it means that you have to reduce your system to very few, small number of variables that you are able to analyze, etc., etc. If you want to model a relatively complex system, then you have the difficulty of maybe it's not so easy to characterize it by a small number of variables. And so having the possibility of the numerical experiment really helped to bridge this gap and to address more complex systems. Now, what I see, for me, the use of AI in science, in particular in physics, in my field, I think that it is it's a major step of computational science. I see it as a step of computational science, but it's a major one because it's something that really opens the way to completely new methods, and actually it's invading. I mean, you barely see one field of physics in which there is no AI at the moment. I mean, it's in experimental physics, AI is used as a tool to identify hidden patterns in data, for instance. When you have astrophysical data and you want to find, these are extremely big data, you want to find some subtle patterns, you use AI to do it. But also now in theory. In theory, you can use it a lot. I mean, quantum chemistry, you have I mean, for people who are physicists here, you can look in condensed matter physics. You have a new sets of variational wave function that you can build using AI that enlarges completely the way you can study a problem of condensed matter physics. So yeah, that's kind of, but maybe we can come back to that later. Please don't hesitate to ask questions. So yeah, I said this new AI, I think it asks at least 3 types of questions: scientific questions, philosophical questions, and questions of society. Not sure if this division between these 3 is always relevant. I think they are intricated actually, but just for the sake of the presentation, I will use it. So I want to start and dedicate a large part of my time to scientific questions because that's my field, that's where I know, etc. But I also want to use these scientific questions in order to address a little bit the other 2 questions that I mentioned. So maybe I should explain briefly, I don't know, and here I really don't know what is our shared knowledge. So if I say things that everybody knows very well, you tell me and I can speed up and go to other things. But I thought I would mention a little bit how these deep networks are working, how they are trained. And so in particular, I think that there is one important ingredient in there, which is called machine learning. So machine learning it's a way in which a machine is trained by itself based on the fact that we present to it some examples. So in order to understand that, I just need to, maybe I will have a small drawing of very, very simple of what is a deep network. So a deep network is made of what is called artificial neurons. An artificial neuron is a very simple logical unit which receives some input, and it receives input from other neurons. So each neuron has a certain level of activity. It could be x1 for neuron 1, x2, x3. And then this level of activity is transferred to the other neuron. So this is mimicking what happens in the brain with the firing of a neuron, sending a spike on an action. But okay, I will not explain the analogy with the brain. Yeah.
What do you mean with the level of activity? Let's say sort of information that moves.
Okay, in the brain that would be really the simplest way is to look at it as okay. The brain is made of neuron. The neuron is a cell. It's a cell which has a membrane, and it has a difference of electric potential between the inside and the outside, 70 millivolt. Okay. This, in a real brain cell, there will be signal coming through dendrite, coming from other neurons, and when they accumulate, it may happen that they trigger a wave of depolarization of the membrane, so an electric signal. And this is sent as a depolarization wave. This is sent as a kind of electric signal which propagates on the axon of the neuron. And then when it propagates, it can make synapses with other neurons which are downstream. And so there is an electric signal. When it arrives at the signal, it releases a neurotransmitter because of the electricity arriving. The neurotransmitter is a molecule that goes through the synapse. It goes through the other dendrite and goes to another neuron. That's okay, neurophysiology in 1 minute, let's say. But that's the idea. And that's how it was kind of conceived, I mean, the idea. And so X is a number which would tell you how many spikes per second there are. So if you have a neuron which is at rest, it spikes very little. But then if you have a neuron which is exposed, you have a neuron, the visual system, and it is exposed to a pattern that is favorable for it, it will start to spike. And so you can register it with an electrode. You put an electrode here, you see the spikes. and x would be the number of spikes per second. Okay, that's how it is in neurophysiology. But for us, it will be just a number. A number that tells you how big is the activity of this guy. Okay, it's a number between 0 and 10. Okay, and then once you have this number, maybe this one is very active, etc., etc. They send this signal to this guy, and there are two things that happen. First of all, these signals, these incoming signals, they are weighted. So because there are these synapses, there are very good synapses which are strong, in which if you send a signal, it will be even reinforced in the bottom. There are weaker synapses, and there are also what is called inhibitory synapses. There are cases in which if this guy is active, maybe it will tend to inhibit the activity of the other one. This depends on the type of neurotransmitter that is sent. And so for us, it's just these weights. Okay, and so what this guy sees, it sees a total signal which is x1 w1 plus x2 w2 plus x3 w3. That is what it receives. And then, depending if this is, so you will have, let me call that, this is the signal x0, that will be the signal of this guy. Depending on what it has received, you will find that x0 is equal to that if this is positive and 0 otherwise. So there is a kind of nonlinear function that is applied. Okay. So if that is, so the detail, I don't want to start a course on the detail of neural network. It would take me a few months. But I mean, what I just want to say is that it's a very simple arithmetics. It's an arithmetics of multiplication and addition. It's not sophisticated math. I mean, the whole deep learning revolution is elementary math, something that you could do in high school, basically. And what is a deep network? A deep network is a network in which you have many neurons as an input. So this could be a representation of an image. Imagine that they are organized in a square thing and they are pixels. So you have 1 million pixels. Each of them is a neuron. And there the activity would be the intensity of the light on each of these pixels. Imagine you have a camera. Okay? And then you have this guy receives signals from all these neurons, another one which receives signals, etc., in a second layer. And then they propagate in a third layer, in a fourth layer, etc., until in the end, you would like to answer some question. Okay? So this is the total machine. And you see that this machine, if you present it an input, it will give you an output. Maybe the output could be, for instance, a simple exercise that nobody knew how to solve. I present you an image and I ask you if there is a cat or a dog on this image. Okay? It was a challenge that people tried a lot to program by themselves standard computer to do that. You know, if you have to do that, you say, oh, I will look if there are some triangular ears and then mustache and then if there is that and that, but maybe it's oriented differently. Do a lot of sophisticated things. Maybe if I have all that, I will say it's a cat. Never worked. Now, what does the machine do? You present it an image, and here you have two outputs. This one will say that this is a dog, and this one will say that it is a cat. Okay? So you want to know what is the strongest of these two, and that's it. The machine depends on what? Okay, there is a global architecture, how many layers, etc., but the only main parameter that you have is the W, the weights, how the activity of this guy influences that other guy. Okay? So the machine implements a function in which you have an input, it associates an output, and this depends on these weights. And the way the machine is trained, so that's called machine learning. The machine will itself, the algorithm of learning of the machine, of training machine, will be to find the best set of weights, all these weights which are there are many of them, such that when you present an image of a cat, it says this one lights up, and when you present an image of the dog, the first one lights up. And that's it. Okay. So there are kind of general structure that you have to implement, etc. But then the training of the machine is based on examples. So you have to present a database which is labeled. It's a database of, let's say in my simple task, I have 100,000 images of cats, 100,000 images of dogs. They have to be labeled. So there is someone on Earth, many people actually, who are paid for analyzing images and labeling them. Not only cats and dogs, but you can imagine weapons and all kinds of things. Imagine all the things that people want to find in images. They need to have people who are poorly paid in order, but they have to label all their life. They label images. Okay? Then you present this system a database with many input images, and for each of them you have someone who has said this is a dog or this is a cat. And then the training will be, I have to adapt these weights so that it performs well on the database. So in general, you start from completely random weights and you have completely random labels. You find a result which is not at all what you want. So what you do is you pick up this weight here and you want to, maybe you increase it a little bit. And you see, does it diminish? If it diminishes the number of errors, you adopt this change. You say, that's a good change. If not, you do not adopt it. And you do that a turn for each of them. Very painful process, very slow. And the big things, the reasons why all this happened now is really twofold. There is the fact that we have now extremely powerful computers which are able to do all these very tedious things, and the fact that we have very big database available. So the fact that there is a world where the web was something crucial. Thanks to the web, you have many images of cats. If you ever wondered why people put images of cats on the web, it was probably because that was useful for training a neural network. Otherwise, I don't know why they do it. But in any case, you have a lot of data, and you have a lot of computer power. But it is still an extremely slow process, and the process of training the machine. So once the machine has been trained, then you have found all these weights, okay, and it performs well on your database. Any image of the database, it tells you that's a cat or a dog. But the good thing is that now you present a new image of an animal that it has never seen, that was not trained upon, and it will generalize. It will tell you with a good accuracy, this is a dog or this is a cat. Same thing with a tumor. You present a skin lesion images, you train it on skin lesion images, you have some which are benign, some which are malign, and train it sufficiently well, and you present a new one and it tells you, with high probability this is malign, you should go to the dermatologist. That's a very important progress. The same thing. Yes?
What is the typical number of layers and of weights of a, let's say, semi-decent program, not the best one? That one would use?
It changes every third month. It is the race, the present progress, the present technological progress is largely based on a very fast increase of the size of the networks that are being used. So I have here, for instance, if I look at ImageNet, which was this program that was segmenting images in 2012, the first breakthrough, ImageNet had 60 million weights, 60 million parameters. So it was already, it's for scientists searching a good solution of this problem in a 60 million dimensional space is already a big challenge. That was 2012. ChatGPT has just the ChatGPT, not the GPT-4, it has 200 billion parameters, 2 × 10⁻11 parameters. the number of operations that are needed in order to train such a network to achieve the task of identifying cats and dogs or tumors or whatever, this number of operations, it has it was doubling every 2 years until the beginning of the 2010, and in recent time it's doubling every 3rd month. So if you look at the number of operations that are done to train these networks, it's much faster than exponential. It's super exponential. The rate of the exponential is increasing fast in time. So now in GPT-3, in order to train such a network, the number of operations that has been made is 10 to the 23. And 10 to the 23 is, as some of you know, it's a mole. It's Avogadro number. It's the number of molecules that you have in an object, in a macroscopic object, basically. So it's an enormous number. And all of the recent progress that you see, the new release of the new chat, the new GPT-4 version, etc., they are based on increasing the size. And increasing the size means increasing a lot the training time, the number of operations that you do for training. So this is something that is, well, it also means that in order to increase, when you increase the size, you need to increase the size of the database. You need to have more data. We are hitting a wall there. We are hitting a wall, and that's a very serious one. It's a wall for the planet on the one hand, because, I mean, is it really reasonable to spend all this energy and in order to train these machines? Is it reasonable to release all the CO2 to train these machines? I read this actually this morning that the 20% of the energy consumption of Ireland, the country, the whole country, 20% is for data centers. Ireland is a hub of data centers because of fiscal things, etc. 20%, sizable thing. So we are going to hit a wall in terms of the resources that are used to train the thing, and also the data. GPT, I will talk about language models. They are trained on data. They are trained on all the text that are available. They swallow all the text that is available on the web, not necessarily with all the authorizations. That's another story. It's not my field, but it's something very important also. But they take everything. Now we hit the wall, because at some point you don't have enough data. You make a 10 times bigger model, but you don't have enough data to train it. So that is another obstacle. So I just wanted to, I mean, again, for the people who are trained in math or physics, optimizing in a space of 1 billion parameter is something that we would have thought is impossible. The function that you want to optimize, which is the number of errors that is made, it's not a convex function, it's not a smooth function, it's a function which is very agitated in a very large dimensional space. The fact that this is doable is a surprise in itself. It's part of the many surprises. So the result is that we have machines that are able to classify. I keep with the cats and dogs. It's stupid, but it's the one which is the shortest to tell. But classify cats and dogs. What is that? That is an image is maybe 1 million pixel, let's say, in entrance. And you have an image is a point in a 1 million dimensional space. And in this space, there are the regions where there are the cats and the region where there are the dogs. And in some sense, you have found a way to separate these regions. Okay? This is something which is a priori mathematically very difficult, because you know, what we are doing here is some kind of interpolation in very large dimension. If you have to interpolate, you know, if you have a function and you have 10 points, okay, you interpolate it with 10 points. Now, you have a function in 2 dimensions, you have to put 10 points in each direction, and you start to interpolate the grid. This means 10 to the 2, 10 squared, it's 100 points. If you have a function in 10 dimensions, 10 points in each dimension, it's 10 to the 10. If you have a function in 1 million dimension, it's 10 to the 1 million. much larger than the number of atoms in the universe or whatever number that you can think of. Okay. So, in principle, something that is extremely difficult to do, and it also relates to some of the difficulties that we have with the result. So I will not explain how really the training is done, etc. But I want to stress one thing which I find interesting in itself, which is, imagine that you take the llama, just to change from ChatGPT. You take a large language model, maybe you take one which is publicly accessible. So you know all the number of layers. For each layer, you know all the weights. So they give you 10 billion, 100 billion weights. You have them in your laptop. So it means that you have this artificial neural network. You know every single element. You know everything. But you don't understand much of how it works. Then you use it. You can train it. You can ask it questions if it's a language model. You can put some prompts and see how it answers. So you can do a lot of experiments. You can see how it fails, where it fails. You can not see how it fails, but you can see where it fails, when it does good answers, etc., etc. You don't know exactly how it works. And so I sometimes call that it's both the dream and the nightmare of the neuroscientist. That is, imagine that you are a neuroscientist. Neuroscience has developed more and more sophisticated tools for analyzing brain activity data, the number of spikes that I was saying before. You can register on multi-electrode, you can do that simultaneously on 1,000 neurons, something unimaginable a few years ago. Fantastic. But now it's not 1 million, it's 100 million, and you know them. And in spite of the fact that you know all of these details, you don't know how it works. The problem is that this processing of information between the image and the label cat or dog, it's an aggregation of information to larger and larger scale. It's something that we call an emergent phenomenon. It's a macroscopic phenomenon coming from very tiny signals. Every single neuron has no knowledge there. It's the accumulation of the information from all of them that gradually builds a representation. And this representation allows you to solve this problem. So the fact that we do not have a good theory of machine learning in deep networks. That's the problem. We have a lot, there are tens of thousands of colleagues working on, or hundreds of thousands working on all this. So we have many more papers than we can ever read. We have many more explanations. We have many more tests, etc. There are a lot of things, but there is nothing like a full theoretical framework that would explain you how it works. It has some very big consequences. The fact that you have no theory, it also means that you have no guarantee. So you have no guarantee of the fact that a classification task will not give you a completely crazy result. In analyzing images, there were perverse colleagues who started to train an image generator so that it could generate images that would fool the best neural network. So you train a neural network, it analyzes cats and dogs, it's perfect, it makes 0% error, exactly as you and me. But then you have this other guy who starts to take a very nice image of a cat that all of us will recognize a cat, puts 10 to the minus 3, 1,000 small change of pixel, 1 in 1,000. Very, very few, but very well tailored. To your eye, the cat is the same as before, not changed at all. And the neural network, which was so smart, you presented this obvious cat. It has not changed. It changed 1 pixel in 1,000. You don't even see it. It is completely fooled. So there is this possibility of generating adversarial example. It's a problem. It's a problem because it just means that you have no control on the limits. You have no control on when things go wrong. And as soon as it's possible to generate adversarial example, you have images, instead of changing 1 pixel in 1,000, people took an image and put a small patch somewhere in the image. So you have an image of a cat and you put a small patch small thing here, like a small rectangle, seems to be gray, etc. But it's tailored in such a way that it will fool the guy. So same thing with, you have a self-driving car, it's analyzing the scene, it has been trained to analyze the stop sign. You put a small patch on the small sign and it's seen as a green light. Okay? And no need to say it, if these patches exist, there will be people to put them on the stop sign. It will be delicious, but there will be people to do it. So the fact that you cannot control all the situation, it's intrinsic to the fact that you have trained this system in a very large dimensional space, and you cannot control what could happen in the corners of this large dimensional space. You have trained it on some typical situation, but not. There was another example of that, which was a self-driving car in Los Angeles that recently, I think they had a few months ago, they had an accident in the following. It was stopped at a red light or something like that. There was another car, and the other car bumped into a pedestrian. The pedestrian fell on the self-driving car. And the self-driving car realized, because it had been programmed well, realized that there was something wrong happening. And it switched to the emergency mode. The emergency mode was pull back and park and stop. So pull back and was dragging this poor guy that had been fallen, and so it was basically harming the poor guy. So that's just related to the fact that these programs, they are analyzing something, but they have no representation of the world. They don't know what is an individual. They don't know what means hurting. They don't, etc. I will come back to that. So what I say is that from the scientific point of view, the fact that we have this problem of emergence means that we have no explanation. When we use a deep network, we can use it as a black box. We can look at what is the input-output function, but we have no explainability. That's a major issue. And we have no guarantee that it will not go crazy in some situation and do crazy things. The second point that I want to stress is that by the nature of the learning process, the machine learning, it inherits all the features of the database. Okay? So in particular, it will inherit all the bias of the database. And it's very sensitive to this bias. And it's very difficult to control this bias because we are in a realm of very, very big data. And basically, because you have the more successful machine, the more powerful machine are the big ones. The big ones need a lot of data. When you have a lot of data, it's not that you are controlling all the data. And even if you would be able to control all the data, what is the right balance? What is the right proportion of images of this type and that type that you should train the model upon? If you don't have the right proportion, whatever it means, I think it means nothing myself. But then you have a lot of bias. There was this famous Amazon was using an AI-based software for recruiting people, and they realized in 2018 that there were biases in favor of men who were identified as more leaders, experienced, etc., while women were more on the task of assistance, help, etc. It was something that was just inherited from all the CVs and analysis of the labeling of the CVs that the machine was trained upon. So basically all the biases that you had in recruiting people from which you generate the database, they are inherited and not controlled and not even aware of. I had an example of that, and that was an interesting one in March. There was some colleague discussing with a large language model and explaining how they have racial linguistic biases. So there was these sentences that were presenting, and one of them was in stranded American English, the other one was in African American English, and they were asking the large language model to complement the sentence. The same thing, you have a prompt and you want to finish the sentence. And so the first sentence that was sent was, the following: I am so happy when I wake up from a bad dream because they feel too real. That was the first sentence. The second sentence was, I be so happy when I wake up from a bad dream because they be feeling too real. Okay? Small variations, but variations that are significant. And it turned out that when you prompt many LLMs, many large language models with that, and you ask it to complement, the first one, they will say, basically they will go towards something, oh, it's a brilliant and intelligent statement. And the second one will say, it's lazy and stupid. This is just statistical. You know, you use this as prompts, you train it, you have to decorate it a little bit, you have to control it, but then it's a very significant prompt, a very significant bias. So the biases, they are inherited, they are amplified, they are not controlled. So that is a very, very big problem. Can I start? Yep. So I think one of I was insisting on this notion of machine learning. I think it's really a conceptual shift, having the machine that learns by itself in some sense. It means that it's very hard to control, but it's also very hard to, as I was saying, it's very hard to understand what it does. And so there was a kind of philosophical discussion that was triggered already a few years ago, and in a kind of premonitory way, by a paper by Chris Anderson in Wired. That was in 2008. It's a paper which is before the new AI. So that's why I say it's premonitory. It was more about data. And the title of his paper was "The End of Theory, the Data Deluge Makes the Scientific Method Obsolete." So this paper is interesting because Chris Anderson is there telling us that with massive data, this old approach of doing science, you make an hypothesis, then make a model, you check it, this old method has become obsolete. There is now another way. I'm quoting him. Huh? I will discuss that. There is now another way. The petabytes allow us to say correlations are enough. And in fact, he says there is no need to understand causality. We can do science just with correlations if we have enough data. So this is a big question because, I mean, at least since Galileo, we have been used to this scientific approach, which is look at the world, make some hypothesis, make some model, check it, and have these loops. So it's the whole scientific attitude which is being challenged in some sense. And Chris Anderson is a kind of extreme position in which he says there is no need for all of that. The correlations are enough. So in some sense, one could say that if I look, for instance, at protein folding, I told you that for me it's one of the main scientific achievements of modern AI. Protein folding is a kind of achievement in the sense of what he says. That is, protein folding is based on the following. Basically, you present a new protein that the system has never seen, and that's the sequence of the protein will be what is shown in the input layer there. And the output will be the shape that it takes when it folds. Okay? There are many, many shapes that are possible. And the system has been, and what is the system basically doing? It has been trained on a database of proteins which should include some similar proteins to the one that you have seen. Okay? And so in some sense it will infer from statistical correlations between the sequence that you give it and the other proteins that are in the database for which we know the folding. From that it will guess what is the folding. So if you look at it, it's a very statistical method. It's a purely statistical method. It's not a method that is so much based on what are the electrostatic forces between the amino acid, how these forces balance, how this mixes with the fluctuating molecules of the solvent, of the water which is around, and all the statistical physics and complicated thermodynamics. Leave that aside. You do some correlation. Your sequence is correlated with that. You deduce that the shape should be that way. And that has, experimentally, that has been more successful than the previous approaches. Still, as I was saying just before the break, I think that it is limited. It is limited for several reasons. It is limited because the resulting device, the resulting program, is not interpretable. There is no explainability of how it comes to this result. You present a sequence, it tells you, well, I think that it will fall this way. So in terms of science, this lack of interpretability is an issue. In terms of technological application, it's not necessarily an issue. For instance, if you want to build a completely new protein that will have the shape like that and that will have, oh, you remember a few years ago everybody knew about the spike molecule that was at the surface of because it was the receptor for the COVID, etc. So if you want to have a new protein, it would have the spike receptors. You want to do that, and you start from scratch. Well, probably screening, not probably, it's obvious, it's already there. Screening a lot of possible sequences in silico on using this kind of thing is a very good tool. Because it will produce for you, it will tell you, oh, this is the best candidate. And then you synthesize it and you see if it does what it wants, what you want. Does it really fall the right shape with the right protein, with the right amino acid exposed on the surface, etc., etc. So this is technologically, it's not necessarily a limitation. From the scientific point of view, I think it is this question of interpretability is a limitation. I have another critics to this. I was asked, actually, I wrote a few years ago, I wrote an article in the French journal Le Débat, which was fully dedicated to this Chris Anderson paper. And I wanted to write a refutation from the point of view of a scientist. So you would say that's because I am trying to defend my field. Okay, it's like that. But I took the point of view, which is usual when you ask this kind of question for scientists. It's point of view of a Gedanken experiment. And my Gedanken experiment was the following. Imagine that you want to have a very good software, a very good program that is able to say, if I throw this object in the air and you look at how I throw it, you look at the first meter of its trajectory and analyzing the shape, etc., etc., you want to know where it will fall. Okay? Imagine that is your goal in life. It's not more stupid than identifying cats and dogs on an image. So you do that, and the new way, the Chris Anderson way, would be, okay, I have a bunch of 10 students who will dedicate their life to making movies of sending objects, seeing how they fall, correlated, and then you feed that in the neural network, and the neural network will be able, when you present a new object, you send it, it will be able to tell you where it falls. Fantastic. Maybe you need to have 50,000 movies registered and burn a kind of lot of energy and emit a lot of CO2, but then you make it. You have achieved something. You have achieved something, and let me even believe that maybe it is as precise as would be the old-style engineer prediction. The old-style engineer prediction would be, oh, I know the law of gravity, I know the shape of the object, I know the laws of friction in the air, I need to know, of course, the density of the air at that point, the temperature, the velocity of wind, etc. But from combining my law of gravity and the laws of friction and the law of Magnus rotation of an object, etc., with all this combination, putting that in a computer, I can predict the trajectory. Imagine for a while that the machine learning tool does as well as the best engineer, maybe better. So that's an achievement. Does it mean that you don't need the scientific method? I'm not so sure. You don't need it if your goal is only to know what happens if I send this pencil, where it will arrive. If you want to do that, you don't need any more. But if you want to understand the world, then I think that the scientific method is still very badly needed, because in the scientific method, instead of having 100 billion parameters that will tell you what is the result, but you don't understand how it does, the scientific method decomposes it. It decomposes it in a way which is, it makes use of, decomposes the whole problem into several problems. There is a problem of gravity. There is a problem of friction. There is a problem with the wind. You decompose all that. For all of this, you need to understand a law, a specific law, and then you need to combine them. Once you have understood all of that, it means that you can first of all, you have an explanation. You have an analysis. With this explanation, you can transpose your problem. If you ask me now, I will go to Mars, and on Mars I will be a robot that will send something. On Mars, what will happen? In Mars, well, the law of gravity is different, but in my scientific method, I know how to change a thing. Just change for the gravity on Mars and I have the result. It's there. If I have the other method, the AI, the machine learning method, I need to send my 10 students on Mars and send them 50,000 more times and retrain the thing. So it's a completely different attitude. So in some sense, I think that there is this whole discussion which is interesting. I am, on the one hand, I am very surprised and admirative of the way the machine learning tools and the deep networks are successful in solving problems that we did not succeed in solving with the traditional scientific method. So that's very important. On the other hand, I think that the right perspective is to think of them as a tool. It's a tool that will help us to develop more deeper theories, better theories, but we still need to develop the theory, because the theory is the way you organize the knowledge. And the knowledge, maybe it's a limitation of our brain, and that's a kind of very philosophical question. That is, in some sense, our brain is limited. You know, you can put in your memory, in the short-term memory, you put 7 objects. If I tell you a telephone number which has 15 digits, you don't memorize it. 7 digits, you memorize it. So this is our limitation. So it means that we have, in the brain, we have a computer which is able to analyze things, but based on a relatively small number of objects. Of course, we have at hand the libraries, the memories, the pen and paper, the books, etc., in order to store many more things and to gather it. But then, so it means that we have to organize the knowledge in such a way that it is what we call in math, it's combinatorial. That is, the complexity comes from combinatorics. It comes from a small number of objects that you combine. So, you know, and the small number of laws that you start to combine. And it is this combination that in the end is able to give you a good picture. Think of, I don't know if there are particle physicists here, but maybe, well, even if not, it's not the problem. You have heard about the standard model of the particle physics. Standard model is an incredible achievement. Something that is, you can write what is called the Lagrangian, basically what describes all the interactions of the fundamental interaction of particles. You can write it on a piece of paper like that. Each element which is contained there, it needs a chapter of a book. And in order to understand what is this element, you know, the Higgs boson, you have the gluons and the quarks and all these things you have to. So for this you already have many books. And for reading these books you need the training of 5 or 6 years of trainings of physics in order to do that. But in the end you have a compact representation. So it is this combinatorics that is able to analyze a very complicated world. And I don't see that one can do a substitute of that with any machine learning. Yet, it is true that machine learning is very efficient. It can be extremely helpful as a tool to identify what are the right variables, for instance, in a complicated situation. And it might be, and this I have no answer to that, it might be that that there are problems which are not reducible to combinations of laws with a small number of elements. Let's say that this combinatoric approach would not work. I don't know if that, and so then it would mean that for these problems there would be only the statistical inference with the big networks would be the solution. And this I don't know, and I think nobody knows if that's the case. But it's a kind of perspective that has been opened by all that. I want to go on in that direction in analyzing analyzing my quotation marks. You remember in my title I said intelligence, and I always put quotation marks on this intelligence. I mean, this is very debated among colleagues, etc. I am in the camp of the people who believe that there is no intelligence at all in the artificial intelligence, whether it is the new one or the old one, actually. Turing, as you know, the Turing test that goes back to the 50s, Turing was saying in order to evaluate the capacity of a machine to think, we have to make it pass the Turing test, which is you discuss with the machine and you're not able to guess whether you're discussing with a machine or with a human. Probably with the language models, we are not that far from passing the Turing test. And still, I would like to argue that these language models or any of these new AI tools, they are very far from any type of intelligence. They have no representation of the world. That is, if you have a tool that is able to, let's say, maybe I have an image analyzer, I show you this image, it tells me it's a glass of water. Does not know what is a glass, that it is an object, or what is water. Does not know that if I do that, I splash the water on my... I don't know if I throw it down, the glass will break. No representation of the world. As Yann Lequin someone says, and I agree with him, a cat that is able to walk on this table has a much, much better representation of the world than any of these algorithms. So they have no notion of causality, no will, no consciousness, no intention. Okay? So, but they are very smart at finding correlations and at making some predictions based on correlations that we don't see. So this is something. So that's my position. At the same time, I must admit, and maybe there are people in the audience actually who are much smarter than them, who know that much better than me, but okay, let me just propose, let's say, some points for the discussions. It's also true that in all these few last decades, we have regularly been pushing our definition of what is intelligence. I mean, and we push it away from what the machine is able to do. That is, I probably, if I would have asked you in 1985, is it a sign of intelligence, the fact that one plays chess very well? Most people would have said yes. And maybe nowadays, if I ask the same thing, most people would say, well, yes, but you know, it's a kind of, it's a set of rules and you apply the rules, not creative, it's not that creative, etc., etc. So we are trying to push the definition of intelligence more towards creativity, or even more than that, towards what makes us singular. So that is human. I mean, we want to have a singularity in the world, and we always believe that intelligence is our singularity. So maybe it's the right time to make give a small chapter on language model. So a language model is a model in which it has been trained, the same kind of training as that, but it is trained on a very, very specific task. the very specific task is the following, that it's called next token prediction. I will say maybe it's like next word prediction. So basically you have an input layer. In an input layer you will present a sentence and it is interrupted. And then you have a lot of layers, you have all the weights, etc. And in the end you want to ask what is the next word. Okay? So maybe I will know, maybe I have at the beginning of the sentence, the cat has jumped. Okay, and you ask, what is the next word? Okay. And for that, what you have used is you have taken all the texts on the web and you have trained your system in order to guess the next word from all this. Okay. So maybe the right output would be, I don't know, out of the window. And then the next step you say, cat has jumped out, and then you say of. Has jumped out of the window, etc., etc. So that is what it is trained. It is trained to complement a sentence, to guess what is the next word. Okay? And it's trained on doing that on a probabilistic basis. That is, if I have the sentence, the cat has jumped, well, you will have several possibilities here. And these possibilities, there could be, I don't know, out, off, in, whatever. I mean, there are a sequence of words. And what this guy will do, it will be trained to assign, given that, it will assign probabilities to each of these next word. And then what it will deliver to you is the one which is the most probable. Most probable based on what it has seen on its training, okay? Based on correlations. So a large language model is just a system which produces a sequence of words, each of which is the most probable one. So that's why when you ask ChatGPT something, you say, in the end you look at it and you say, well, it's a bit average. It has been trained to be average. It has been trained to be the most probable thing, not been trained to be original, to be a thinker. And so you see that when you do that, it's a purely probabilistic model. The language model who does that, I will come back to the guy. The language model who does that has no notion of what is a cat, no notion of what is a jump. Nothing. Not at all. Purely probabilistic. By the way, Shannon himself, who was one of the fathers of the theory of information, he had played this game. He had looked at language, English, and he was trying to complement. And he was trying to generate sentences based on that. He had available, I don't remember on what he trained it. Did it? Well, basically with the data that he had available, he could look at something like maybe 4 words, the 4 previous words. Okay? And based on the 4 previous words, he had the statistics and he generated a new one. And he generates sentences like that. These sentences make no sense at all. Okay? When you do that. So the new trick that has been the big development of artificial intelligence for large language model is that you have been able to enlarge completely the sentence, not only looking at the 5 last words, but looking at maybe 1,000, 2,000. From a mathematical point of view, if you have a sequence of 2,000 previous words, guessing the next one, of course it will be much more accurate. But the number of combination of 2,000 words that exists, it's much, much larger than anything that has been written on the web. So you don't have the statistics, you don't have the probabilities from the web. So you need some tools, and there is a tool which will a tool which has been invented, which is called the attention mechanism. The attention mechanism will tell you, you will not, maybe you will pay attention to the last 3 words, but maybe there will be some words which come before, which are very important, and that's in order to guess the next one. Maybe there was window that appeared before or something. And you have to focus your attention not on all the 1,000 words, because it's impossible, but on the 10 most significant ones in this 1,000. So that is called the attention mechanism. It's used for training. Okay. So this is a language model. I insist on it. It's a program that generates a sequence of words in which each word is the most probable one given what has appeared before. It has been trained like that. Okay? The big surprise is that this produces texts which are correct synthetically and semantically. This is a very big surprise. And this is a big surprise. I don't know, maybe there are experts in language modeling in the audience, I don't know, but I mean, one has to realize that it's an old, it's not a very old science, but quite a few decades old science, the science of language modeling. And in this science, there has been a lot of theory which has been done, you know, a lot of analyzing the rules of the grammar, of the syntax. It's something that all the rules of the syntax of all the natural languages, Chomsky, etc., there have been a lot of sophisticated analysis. Using all these sophisticated analysis, nobody so far had been able to generate sentences that had this level of correctness, both synthetic, from the point of view of syntax and of semantics. So it's a big achievement, another of Chris Anderson's victory, in some sense. These texts that are produced, they are, in some sense, they are very standardized. They are I call them the expression of a social consensus, in some sense, because they are the average answer. They are the most probable sequence of words. Okay. So, in some sense, for very standardized texts, they are perfect. If you want to write a recommendation letter for a student, you can use it this way. I have taken myself these days, I write recommendation which are exactly the opposite. That is, I take it very short, totally factual, 5 lines, and with strong argument, and just to be clear that it has not been written by ChatGPT. But if you want to have it, I mean, the last mail that I received from a student applying for a postdoc, it had in itself, oh yeah, you know this story. It had in the second line, dwell. You know dwell? Dwell is this word that is a signal of ChatGPT. For some reason of the training of ChatGPT, it uses dwell much more than it used to be in standard English. And by the way, the analysis of the occurrence of dwell in the scientific abstracts of scientific paper, it's there, and at some time in the last year, starts to boom. Okay, so it means that we, us, not me, but some people use ChatGPT to produce the abstract. Okay, so the thing that I want to insist upon, so I think it's very interesting. It's very interesting to see that, and I will do the same thing for language as has been done for the intelligence, for chess, etc. They will start to argue that in the end, maybe language is something extremely artificial, very codified, and which is not so much related to intelligence. That's a risky way, but I mean, I have to take risks just to prompt the conversations at lunchtime. And first of all, before going into that, I want to discuss a little bit the question of bullshit. There was maybe, who knows the small book of Harry Frankfurt on bullshit? 2 persons. So for those of you who don't know it, I recommend it. It's an interesting book. I find it interesting basically because of its topic, and I find it up to date now, particularly. It's called On Bullshit, and the topic is really to try to analyze, let's say, what is bullshit. So bullshit is, maybe I read the first page so that you understand what his book is about, and then I will comment it in the context of large language models. One of the most salient features of our culture is that there is so much bullshit. Everyone knows this. Each of us contributes his share. But we tend to take the situation for granted. Most people are rather confident of their ability to recognize bullshit and to avoid being taken in by it. So the phenomenon has not aroused much deliberate concern, nor attracted much sustained inquiry. In consequence, we have no clear understanding of what bullshit is, why there is so much of it, or what function it serves. And we lack a conscientiously developed appreciation of what it means to us. In other words, we have no theory. I propose to begin the development of a theoretical understanding of bullshit, etc., etc. So that is his venture, and then he starts to kind of make quite a few examples. So bullshit non so come si traduce in italiano, tutti hanno stronzate. Dunque, we are talking about stronzate. But I mean, I don't know about the stronzate in Italiano, but I think that bullshit in French it could be translated as connerie, but it's not exactly the same. So I mean, the positioning of the language is not.
En français, connerie, c'est mieux. En français, ça sonne mieux.
En français, ça sonne mieux.
Connerie, ça va.
I don't like it. I don't like it either. I'm not sure I like bullshit either. So there was a paper recently, a few months ago, by Michael Townsend Hicks, James Humphreys, and Joe Slatter from Glasgow University, and the paper is entitled. Well, it's entitled "ChatGPT is bullshit." Okay. So it's appeared in Ethics and Information Technology. And of course, the whole paper is positioned with respect to the on-bullshit of Harry Frankfurt. It's a long discussion. I will not go into the details of it. But basically, the idea is what they make is a distinction based on Frankfurt by a bit re-elaborated with their own words. And their distinction they want to distinguish three types of bullshit. There would be the general bullshit. General bullshit would be any utterance produced where a speaker has indifference towards the truth of the utterance.
Can you repeat this?
Any utterance, any expression produced where a speaker has indifference and is indifferent towards the truth of the utterance. The truth does not matter. Okay? Hard bullshit. Hard bullshit is bullshit produced with the intention to mislead the audience about the utterer's agenda. Soft bullshit. Bullshit produced without the intention to mislead the audience about the agenda. Okay? Very simple categories. It's not exactly like that in Frankfurt, but that's what they use. And needless to say, their conclusion is that they have two conclusions. The first conclusion is that ChatGPT is a soft bullshitter. And this is quite clear. Maybe I quote them. 1 second. I am able to. Okay. I quote them. The basic architecture of these models, they are speaking of large language models here. Basic architecture of these models reveal this. They are designed to come up with a likely continuation of a string of text. That's what I have explained. It's reasonable to assume that one way of being a likely continuation of a text is by being true. If humans are roughly more accurate than chance, then true sentences will be more likely than false ones. Okay? This might make the chatbot more accurate than chance, but it does not give the chatbot any intention to convey truth. This is similar to standard cases of human bullshitters who don't care whether their utterances are true. Good bullshit often contains some degree of truth. That's part of what makes it convincing. Okay? So it is very clear that a large language model, a ChatGPT, etc., is bullshitting in the sense that it produces a sentence which is correct. Again, it's a big surprise. It's a wonderful achievement. I mean, being able to build a sentence like that automatically, which is correct. Correct grammatically, semantically, etc. It does not carry any information on truth. There is no notion of truth in ChatGPT. It's a sequence of most probable words. So there is the notion of truth does not matter. So it's certainly a bullshitter. There is no. Then they will discuss, is ChatGPT a hard bullshitter? A critic might object. It is simply inappropriate to think of programs like ChatGPT as hard bullshitters because 1, they are not agents or relatedly, 2, they do not and cannot intend anything whatsoever. We think this is too fast. First, whether or not ChatGPT has agency, its creators and users do. So they will argue that ChatGPT in itself is not a hard bullshitter, but that it is a bullshit machine. It's a bullshit machine that creates something, creates sentences, utterance, as they say, which aims at faking to be real, at faking to be human. And in that sense, it aims at really lying to the people who are using it. In that sense, it could be hard bullshit. I think it goes a bit fast. It goes a bit too far away. But I will certainly agree with the fact that it is a bullshitter. This is absolutely obvious. The thing that is quite remarkable is that it is a bullshitter that nevertheless can write texts which are of good quality, technically. I remember when ChatGPT came out, I asked it, please write for me, I want to write an op-ed that I want to submit to the New York Times about the danger of killer robots. Killer robots is an issue, and I had one sentence, I said, killer robots with the new AI become extremely dangerous because there is a possibility to make the autonomous decision of killing. I think they should be banned, and please write an op-ed for that. It produced for me, in 3 seconds, the perfect op-ed. It's clear that it had digested all the op-ed in the New York Times, the Washington Post, etc. It had the right format, paragraph with the 3 sentences, well separated, good arguments, an English infinitely better than mine. It was just perfect. Okay? Very standardized thing. And so the fact is that when we read that, we have this tendency, which is really something which is inherent to our history of human being. We have the tendency when we read a text to think that it has been written with intention. I mean, so far, until last year, all the texts that had been written were written with some intention. It might be the intention of a hard bullshitter, by the way. That happens. We have all examples of that. But there was an intention. And we have been trained, reading text for millennia, we have been trained to, when we see a text, we see an intention. We try to decipher the intention. That's part of our training. We are not even conscious of that. But that is very clear that when we start to interact with ChatGPT, we start to think that there is an intention behind. We very easily lose track, if ever we knew it. Most people don't know that, but people lose, if they knew it, they lose track, or the other case, they didn't even think that it is a sequence of words which are more probable, and that's it. So there is no representation of the world, there is no intention, there is no a relation to reality, no relation to truth, no relation to consciousness, nothing. It's empty. It's pure bullshit. And it can be very good. So that's a kind of challenge. I think that I am not at all, although I just said that it is bullshit, I don't say it in a pejorative sense. Again, I want to insist that I think that it's an achievement. For instance, for the students, I'm not at all against the use of ChatGPT, but I am in favor of the critical use of large language models. Critical use is the fact that you are able to see what comes out, spot that it is average, poor, etc., interact with the right prompts in order to enrich it, and in the end, after a whole process, maybe make the last small change and endorse it and say, this is a text that is endorsed by Marc Mézard. Maybe he has been helped for that using ChatGPT, but in the end, I have been using spelling correctors for years, and okay, the spelling errors they are my fault, but I mean, I think it is the same thing. That is, at some point, the fact of endorsing it means that the text that is produced, that was pure bullshit, now it becomes an intention.
Your pure bullshit. It's your.
It might be my pure bullshit if the text is bullshit, but the things which are written now they convey an intention. They convey a certain meaning. They convey something on which you can elaborate. Okay? So I think that this is what is happening at the moment with the language model. It is also, sorry, just 1 second, I want to, yeah. So the big surprise, just to summarize, the big surprise is that we are able to generate text which is correct. From the grammatical point of view, it is being used, it will be used everywhere. There is a risk of using it for having very fast generation of fake news, and not only text, images isn't the same thing, etc. I use a lot of text. Is it exactly like, I don't know, the invention of the calculator? You know, when I was a kid, there was no electronic calculator. We had to do the operations by hand. And then there came the calculator, and then people said, well, but nobody will be able to do a computation by hand. It's a tragedy because it's a loss. Is it? Okay. So I think it will still be the capacity of keeping a critical mind on what is written, identifying that this is pure bullshit, or that it contains information, that it can be used to convey information, is something for which we still need the training of people who have been trained to write essays by themselves. So that will be a necessary training. Same way that probably to understand what are multiplications, etc., at some point you need to have done some in order to see what it is. But then maybe we will be using large language model tools, probably in a couple of decades from now, on a completely regular basis without even noticing it. That's quite possible. There was a very interesting paper, another paper I want to mention last year. It's a paper by Kyle Mahovald, Anna Ivanova, Idan Blank, Nancy Kanwisher, Joshua Tenenbaum, and Evelina Fodorenko. Most of them at MIT, but also Texas and UCLA. And the title of the paper says it all. It says, Dissociating Language and Thought in Large Language Models, a Cognitive Perspective. And so their argument is really that language has completely two different aspects, and one has to be able to carefully disentangle these two aspects. Let me quote a little bit of their abstract. We want to consider the performance on two different aspects of language use. First of all, the formal linguistic competence, which includes knowledge of rules and patterns of a given language. And secondly, functional linguistic competence, a host of cognitive abilities required for language understanding and use in the real world. Drawing on evidence from cognitive neuroscience, we show that formal competence in humans relies on specialized language processing mechanisms, whereas functional competence recruits multiple extra-linguistic capacities that comprise human thought, such as formal reasoning, world knowledge, situation modeling, and social cognition. Okay? So they start to distinguish really the language as a set of formal rules, and the language as a functional tool that is used. It is we know that. I mean, neuroscientists know that. Neuroscientists and medical doctors know that. The area of language, when it is when you have it's here, I think. When you hit the area of language where you have a brain, we are wounded in the brain in the area of language, you lose the ability to use the language completely. Still, someone who has that disability of language can compose music, play chess, reason, etc. He's not lost his intelligence. So, language is not intelligence. Language is a tool. It's a tool that we use. We tend to assimilate it because, especially in the academic world, we have the tendency to associate intelligence with language because we spend our time, like I'm doing this morning, communicating with each other, trying to express things through language. And so the tool, which is the language, starts to be assimilated with something which is much more functional than it really is. And so the large language models, they have made a big progress in the formal, what they call here the formal linguistic competence. But not at all on the second part, which is a functional linguistic competence, which is how to use mobilized language in activities, deduction, etc., etc. This is not the case. Okay? So this is maybe what I wanted to say more on the philosophical side. I would have had, but I just mentioned, let's say, that I had this chapter on AI and society, which would be more oriented towards social science in some sense, which is, I think, also a very interesting moment. In some sense, we could say that maybe we are witnessing, it started already a few decades ago, but we are witnessing a revolution of information. Started a few decades ago, but it can be put in perspective with the energy revolution of the 19th century. Okay, 19th century is a moment in which we start to 19th century we start to have machines which produce energy, and these machines, they can be substituted. By the way, I don't know if you have this order of magnitudes in the mind, but it's interesting to know that my consumption of energy, myself here, or when in my everyday life, I consume as much energy as I would if I would have 500 persons working physically full-time for me to produce the energy that I consume. And the same for each of you. Okay, so in a society of slaves, each of us would need 500 slaves, let's say, to produce the energy that we are using for our daily life. Okay? So clearly, the availability of cheap energy, of a lot of cheap energy of chemical or physical nature, has changed completely the organization of work, organization of the society since the 19th century. Now we have the society of information. We have seen it starting with the arrival of, first of all, of the computers, of the personal computer, then on the web, and now AI, which I see as each of them, I see it as a step, let's say, in that construction. It means that we are also shifting towards an information that initially we needed to have the information in the mind, in the memory. Think of the antiquity. Most of the information was in the mind of the people. It was in the mind of the people. In fact, it means that all the production was produced in terms of some kind of, let's say, epic poems, etc., which are ways in which you can memorize a lot of things. We have a poetic structure with its rhythm, also with the maybe singing it, etc. It's a nice way to memorize things. I remember when I used to sing and I was a singer, it was much easier to memorize a piece simultaneously with the music. You memorize the words simultaneously with the music and with the body. And that's much better. Okay, so that was the whole thing. And then gradually there is, of course, written information. You start to be able to write the information, so you can store it somewhere. Then there is a revolution of having the written information broadcast and multiplied by printing, let's say. And then recently we start to have the information at disposition everywhere. And each of us has the whole libraries, etc., in the pocket now. So it means that we can free our mind from memorizing and maybe use it for more noble tasks, because some elements of the memory we can mobilize. Okay? That's a very optimistic view. My impression is that mankind is not going exactly that direction, that the freed capacities of the mind are not on average used so much in such a clever way. So anyway, going back to social science, I think that the reorganization of the work that is at stakes at the moment will be a very important one. It's very important to advocate, to explain to people what it is about. I think that everybody should know about what is a large language model. All these people who will use it in their everyday life, they should know that. Because when you know that it can tell you completely crazy things from the point of view of the information. There is no truth. So you should reread it carefully. I remember I once, at the very beginning, I told my son, who is in the US, 32 years old, and I told him, did you try ChatGPT, etc.? And he said, oh, yeah, I have to make a presentation. I will ask him some information for my presentation of next week. And I told him, never! You give it the information and you tell it, make the nice words and the nice wording of it around it. That he knows how to do. Information does not know. Okay? No truth. So knowing that is very important. So please, let us all go and advocate that for every user, and there will be users everywhere. Everybody will be using it. If people don't know, and it's something that in this paper, sorry, I'm going erratically, but that's nice. I like going erratically. In this paper by Hicks et al. About ChatGPT as a soft bullshitter, they insist on one thing, and I think it's a very relevant statement. They tell you, what is the word that is being used when a large language model gives you nonsense? No, there are a lot of nonsense in large language model. For instance, mathematicians, they like to ask questions like, I give you two numbers, 9.20, no, what is it? 9.9 and 9.11. 9.9 and 9.11, which is the largest one. And the stupid guys, the ChatGPT will answer it's 9.11, because in some sense it has no reasoning, etc. But by correlation, it has understood that 11 is larger than 9. So it does not understand that 9.9 is 9.90, which is larger than 9.11, etc. So this is a kind, and so you know how it is referred to? It's referred in the literature, all of us, we use that. It says, oh, these are hallucinations. Hallucinations, it carries a lot of meaning. When someone uses that, when a colleague uses that saying, oh, it has hallucination, it means that when it's tempted again to fall into this trap, which is to think that the producer of these sentences has an intention, a representation of the world, etc., which it does, and that for some reason it was hallucinated. It had a small glitch in something that did not go well in the brain. That is a very dangerous way of referring to things. It's as if it was a small mistake that we do when we hallucinate. In fact, it's a total misrepresentation. The thing is bullshitting. Okay, so I think that there are a lot of specific risks of a generative model which are like that. So there is a whole problem of biases, inequalities, social justice, the numerical gap which will broaden, and added to that there are a question of robustness, security, and the specific risk of generative model, which is how does a society control, is it possible at all to control all the fake news that can be generated at high speed with generative models. And this, I must say that on that point of view, on a kind of, let's say, slightly political side, I'm very worried about that, because I don't know how we will do. I don't know how to have democracies live in a world in which we have such fast factories of generating fake news. It's impossible. It means that each of us, I think, but each of us on the earth will more and more rely on some sources of information which he or she trusts. But if these sources of information, they have information which do not overlap, which are talking of completely different world. There are, I don't know, supporters of Trump who think that this and that. They have a representation of the world which is completely different from mine. I think that what they say is nonsense. It's total nonsense. That never existed. Okay? But they have journals, etc., which say that. So if more and more, because of the existence of fake news, we have to rely on one source of information that we trust, and this source of information, they do not overlap, how do you make a debate? You make a debate which it's not possible because we don't have the same premises. You don't have the same analysis of what is the world, not even talking about how you want to transform it, politics, but what is it? So that is, I think, it's for me, it is a very big concern, let's say. So I have just, I think I am running late. I have to stop, but.